Hi, now we are going to talk about classification matrix. So again, before we start, we'll just import all the modules that is required for this class, right? And here, so what we'll see in this lecture, basically we'll see like we always use the accuracy functions, right, to check whether this machine learning model, specifically this classified, like the machine learning model which does the classifications is good or not, right? So we'll decide here in this lecture, we'll see why accuracy is not always the best matrix to check the ML accuracy, right? We'll again explain the different component of confusion matrix. We'll define the precision recall F1 score. We'll use to evaluate the different classifier. We'll also see the macro average and the weighted average. We'll also discuss and interpret how to use this PR curve or the precision recall curve. And we'll talk about this average precision score. And then after we'll also talk about this ROC curve and then ROC AUC score. After that, in the last, we'll discuss about how to deal with the imbalanced data, right? And how to use this class weight parameter to deal with the imbalanced data, right? So we have a lot to learn, right? So let's get started. First, for the demonstration, right? Here we have downloaded our data. So here we are loading our data, which is a credit card data set, right? Now we want to classify whether this particular object or the particular person is a fraudulent or the particular transaction is fraudulent or not, right? Here we can see the amount of data we have. We have a good size of data, right? And for the confidential reason, we have only the PCA version of the data, not the exact uh, the column of the data. We can check the info of the data, like we can see like the basic information. So we can see there is no missing value, right? And here we also have this time data set, like the time column. We also have this amount in the classes column, right? Now we can check the describe, which will tell you the mean, standard, minimum, and all these value, right? Now here, we do not have the categorical features, so all the feature we have is in numeric, right? And we have to be careful by using time in the amount feature. So we can scale the amount feature, but what about time? For now, in this lecture, we'll just drop our time data set, right? We'll not deal with, like, we'll not discuss much about how to deal with the time. Maybe we will discuss more about time in the later video, right? So first we'll separate our data into training and testing. So here we have this training data set. So here we have separated our, so here we have separated into training and testing. After that, we have again took the X and the Y part of the training data set, which we call this is an X train big and a Y train big. And then from test data set as well, we have separated X and the Y part, right? Now, now it is easier to demonstrate the evaluation matrix using explicit validation set instead of cross validation. So here let's use the cross validation, but for that here we are again dividing our this train big data set into a two-part training and the validation, right? And now first we are trying our baseline model. So our baseline model says our train accuracy is 99% and our test accuracy is also 99%. Now till now, we have never tested a model which is giving the 99% of the accuracy. But here we can see that we have got the 99% of the accuracy. This dummy classifier is giving you the very good result. So what should we do? Should we just be happy and like deploy this dummy classifier model? So before we take any decision, let's take the class distribution of the classes. So here when we check the class distribution, what do I say? Oh, so now we can see that now 99% of the data is the zero or like non-fraudulent transaction, and only 0.00717% of the data is the fraudulent transaction, right? So it's like 0.17% of the data is fraudulent transaction and 99% of the data is non-fraudulent transactions. So we have a huge gap between both classes. So we have the meaning non-fraud transactions, but we have only few transactions which are fraud, right? And here we have used, when we build the dummy classifier, it have used the most frequent uh, method to build the dummy classifier, and the most frequent is the non-fraud. So now when we deploy this model, what will happen is, when we deploy this model, so most of the data, so because most of the data is non-fraud, so it will, this model will always say as a transaction as a non-fraud. So it will not look out whether this transaction is a fraud or not. It will simply say it is a non-fraud transaction, because this is what a most frequent dummy classifier does. Right? But our important class is the fraud transaction class. We want to spot all the transactions which are fraud. We are not very much interested in the non-fraud transactions. Now, before we try logistic regression, let's create a pipeline. Here in the pipeline, we have used the standard scaler. We have used the logistic regression, the cross validation. Here we have used the cross validation. We have passed the pipe. This is the, now with the standards, with the scaled data and the logistic regression, we are seeing a slight improvement in our accuracy, right? So now our model is, earlier our model was 98% or 99.8 something percent, but now we have 99.9 something percent. So we have the 0.01% of the improvement. But what score should be considered as an acceptable score over here? Like with this 99.91%, is actually spotting all the fraud transaction or not? This is what our like, this is what we want to consider, right? We want to spot all the fraud transactions. We do not want to leave any of the fraud transactions. That is what our goal is. At least for now, this is our goal. So when we check, when we do the cross validation, we have got this accuracy as this. So when we do dot score functions, when we apply this dot score, by default, it uses the accuracy functions. What is accuracy formula? It's like predicted value divided by total value. So it will be the total predictions divided by the total example. Correct prediction divided by the total examples. So again, we know that our data has 99.83% as a non-fraud, and only handful of the example as a fraud. So all these example will be considered as, will be correct, right? We are only looking at whether we are capturing this example as a correct or not. So here we can see that, right? As in total, we have, at least we have predicted most of the example as a fraud, because of the class imbalance data we have, and the total number of example will divide by that, and that is the value we are getting. So using this formula, we are getting 99.91% accuracy. So the question is, should we use this accuracy function, or is there anything that can give us more informative result? So now let's dig deeper. Now we'll talk about confusion matrix. So the so this confusion matrix, basically it's a way to understand all the error in a different way. So in confusion matrix, we have two things. So first we have as a false positive, which we call as a type 1 error, and then the second error that we can look as a false negative. We can look at this two type of error, false positive and false negative. And in statistics, we call false positive as a type 1 error and false negative as type 2 error. Now, when this type 1 error happens, so when again this type 1 error is like, it's like this type 1 and type 2 error is like, understanding this is a difficult, but when you look at this term like the false positive, this means that our model is falsely saying this example is a positive, but in reality this example is negative. That is how you should look at, right? So false positive means this examples like your model has taken as an example, and those example which was labeled as a fraud, and but it is not fraud. That is what the false positive is. Here our positive example is the fraud example, and false negative means when our model makes a mistake and says it's non-fraud, but in reality it's a fraud, right? That is what the false negative is. So we can look at this, the percentage of false positive error that that model is making and the percentage of false negative error that model is making. First we'll fit the model. So here we have this model here. To build the confusion matrix, we'll import the confusion matrix, right? We'll apply the predict method on the validation data, and then so this will give you the total predictions. Now we can now we can give in the confusion matrix, we can give the original value and the prediction value. That will give you all the like all these parts. So basically it will give you the true negative, false positive, false negative, and true positive. And you can plot. So this function is there. You can plot with this function. Here we can see that according to this, right? Now this term is called the for true negative, and this term is called true positive, right? So we have to look off. So basically this is a diagonal and this is off diagonal. So we have to look this off diagonal. So all the off diagonal is basically it's uh, like it's it's a wrongly predicted value. So this one is the false positive and this one is the false negative, right? So by looking at this, we can see that like, and here we can also see this. So it's like here we can see that it's a true not fraud. So it's a true not fraud and true fraud. So basically the total true not fraud example is this plus this. So the total non-fraud example is this plus this, and total fraud example is this plus this. And here the model has predicted non-fraud as in this plus this. So this many example has model has predicted as a non-fraud, right? And the model has predicted a fraud as in this plus this, right? So here our model, so here we can see that. So basically this is like total false positive. So here our model says that mm, this 9 example is not fraud, but model has predicted as a fraud, right? And here our model says that this many example is fraud, but the model has predicted not fraud. Now here our model is making lot of mistake in predicting non-fraud, in detecting non-fraud. So model is not able to detect the actual non-fraud, right? So we have this 39 example which is fraud, but model is saying it's not fraud. So a lot of like a lot of examples is is kind of hurting over here, right? Now this breakdown we can get with the help of confusion matrix, right? Now so basically we can see all the off diagonal, which is the actual value we have, right? So what is positive and negative? This is, as a human we have to decide which example, which class can behave as a positive and which class can behave as a negative. So we have the two kind of binary classification problem. One is we have to distinguish between two classes, whether this is class A and the class B. And the second type of problem is we have to detect whether it is a fraud transaction and non-fraud transaction. Whether do we have to spot the spam or not? We have to spot the disease or not, right? Now, in case of spotting problems, right, the things we are interested in spotting the positive class. Basically, mostly we want to detect the positive class. We want to detect all the fraud transactions, right? Now here we can also get the actual value. Here we are printing all the actual value as a confusion matrix. So this is like true negative, this is like false positive, this is like false negative, and this is like true positive, right? Now we can see confusion matrix with cross validations. We can also apply confusion matrix with cross validation, right? So here we can use this cross val predict method, right? So here we are using cross-value predict method. Basically, this will take the pipeline and it will return you the output of the validation data, right? And here we are passing the actual Y value. This is the confusion matrix we are getting with the cross validations. With the help of cross validation, how the confusion matrix we are getting, this is the output we are getting. Now we know that accuracy is not always a good option. So we can break down and look at the confusion matrix. But now let's see some more terms which is related to confusion matrix value, like the true positive, true negative, false positive, and false negative. So now we'll talk about precision recall and F1 score. Now, so till now we have been using as in score functions, basically which uses by default the accuracy method, right, to give you the accuracy of the model. But now we know that accuracy can be misleading if we have the imbalance, or if we have the class distributions not balanced, right? Now we need some other matrices to assess our model then, right? If we have the imbalanced data set, that means we need some more matrices to kind of check our model accuracy. Now we'll discuss these three common matrices called recall, precision, and F1 score, right? Now later we'll also talk about few other method, and like later we'll also discuss about how to deal with the imbalanced data set. But first, let's use the confusion matrix with the simple pipeline. We are applying the fit method, we are applying the predict method, and then we are using the like here we are using the confusion matrix, right? So this is the value that we are getting. Now we know that confusion matrix gives you the part of our predictions. It gives you the true negative, false negative, and true positive, right? Now, what the recall is. So basically, so when we talk about the recall, here first we're talking about the recall, right? So when we talk about the recall, so recall is basically, we look at that. So when we check the recall, basically it checks among all positive example, how many did we identify? So let's say that if you are interested in all the positive examples, if you are interested in to kind of building a model with the higher accuracy, right? Or building a model where a model can detect all our fraud transactions. In that case, we can check this recall. So recall is a matrix which will check, like, if among all the positive example, how many did we identify? That means we are identifying how much percentage of the positive example. It really focus on the positive examples. So this is the formula looks like for the recall. So the recall formula is true positive, which is the number of positive example predicted by the model divided by all the positive examples, right? So it's like true positive divided by the positive, all the positive examples. So here is the true positive we have. So the total true positive is, so, and how many example has been predicted as an, so this is the fraud that we are saying, right? So it's like true positive, this 36 divided by 39 plus 36 in this case, right? This is what the recall does. Again, we can check the accuracy. So we can check the percentage of recall. It's a 63%. So the percentage of recall is 63%. Here we can check. So the true positive is this much, false negative is this much, right? And now we can check the recall is 61%. Now, what is precision? So precision checks. So again, till now, like earlier we had discussed that we are interested in how we are detecting the fraud examples. So precision tells you among the positive example you identified, how many were actually positive. That means, so in the recall, we had among all the positive examples, how many did you identify? So it's like true positive divided by true positive plus false negative, right? And precision tells you among the positive example you identified. So how many positive example we identified? So here we have identified total 36 plus 9 as a positive example. Our model says this 36 plus 9 as a positive examples. So whatever the positive example you have identified, in that, how many were actually positive? So it will be true positive divided by true positive plus false positive. So here these are false positive. These are false positive. True positive divided by false positive, right? So true positive divided by true positive plus false positive. So precision will tell you if you have identified whatever the example you have identified as a positive, how much is the percentage of that predictions, right? That is what the precision will tell. And the recall will tell is among all the examples, how many examples is you have predicted as a positive. And the recall will tell you what were the predicted value, what were the positive example you have predicted. Out of those, how many example is actually positive and what are the percentage of that predictions, right? So both are totally different matrices. So this is what our precision does. So here our precision is 87%, right? First, our model is only detecting 61% of the positive example. Now, in that 61% of the positive example, only 87% of the positive example is correct predictions. Okay, not all 61% of the example is positive, right? And what is F1 score? So F1 score basically it's a combination of this precision and recall, right? And like we can use this F1 score. Basically, it's like harmonic mean between precision and recall, and this is the formula looks like. So if you are looking for 1 point summary to kind of, let's say that if you want to check whether this how this model is performing, you can use F1 score. That F1 score will help you to do the hyperparameter optimizations, right? Let's say that if you have a model and then you want to set or you want to find a good set of hyperparameter for that model, then we can use the F1 score. So here if we are only talking about one model, right? Not many models. So in one model, if you want to try, if you want to do the hyperparameter optimization, we can use F1 score, right? And here's a formula of F1 score. So the again here's a formula of F1 score is, and the 72% of the F1 score that we have got. So it's a combination of precision and recall, right? And here we have appended all the values. So we have done this task manually. 99.91% as an accuracy, 0.0008% as an error, precision is 87, recall is 61, and F1 score is 72. Now you do not need to remember this formula. You just need to know what the precision, what the recall does. But you can get this output by using scikit-learn. So scikit-learn also has all these functions which has this implementation. So if you want to check the accuracy, you will get the accuracy score. If you want to check the F1 score, you need to use the F1 score. If you want to choose the precision, we have to do the following inputs. So here we are using this formula to kind of check the output of all this is. So basically we are calculating all this using scikit-learn matrices formula, and again we can check that here we have got the same output with the scikit-learn as well, right? Always remember when you use the matrices, which value you have to pass. So first we have to pass the actual value and then you have to pass the predicted value in everywhere, right? Now we also have something called classification report, which is a convenient function, right? Basically it will calculate everything. So this classification report, basically it will give you the all the report of the classes, right? When we check the classes, we have the two classes in this. We have the 0 class and the 1 class. Here we can import the classification report, and we are using our classification report over here. First we are passing the actual value, then the predicted value, and then 0 is called the non fraud, so we are giving the target name as a non-fraud and one as a fraud, so one as a fraud that we are giving. When you print it, you will see this as a classification report. You will see the precision value, you'll see the recall, you'll see the F1 score, you'll see the supports. So support is what? Basically, it is just the data points, right? So here our precision, so again, this is the not the exact value, but this is the approximate like round off value that we are getting. So according to round off, our non-fraud accuracy is 100% and our fraud accuracy is 88%. So sorry, non-fraud precision is 100%, right? Because here we are looking in terms of the fraud, right? So our, again, when we say this, so when we got this output, when we got this output, when we said the recall is 0.61%, right? But it, after the round off, it is a 62%, right? Now this 62% is giving you the accuracy or the recall for the fraud. So whatever the calculation you are doing, this is for the fraud, that we are capturing the 62% of the fraud, right? And here we can see that, right? We are looking at the 62% of the fraud. This is the 88% of the precision, 72% of the F1 score, and the total number of the fraud is 102. Accuracy we are getting is 100%. Then we have the macro average and the weighted average. We'll see about that. So what is macro average? So this macro average gives equal, so basically here we give the equal importance to all classes and average over all the classes. So for instance, in example above, recall for the non-fraud is 100% and the fraud, so this is the recall and the fraud is 62% or 63% approximately. So macro average is 0.81%. So here, when you calculate the macro average, we give equal importance to all classes and average over all the classes. So here, it just, so we are getting macro average of 94%. Basically, we have just taken the average of this value and this value, which we are getting as 92%. So macro average is an average of this precisions, right? So here, like here, we have got the macro average for the precision, recall, and F1 score as well, right? So we do not give a special importance. Like here, we are not giving the fraud as a more important than the non-fraud. We are giving the equal importance. And what is weighted average? So it's a weighted by the number of sample in each classes. So here, weighted average gives you the weighted parameter. So whichever class has the highest weight, that will be like that will have the more weightage, right? So weighted average is decided by the number of samples in each classes and then divided by the total number of samples, right? So that is what the weighted average is. So as in summary, what we know. So now we know accuracy is misleading if you have the imbalanced data set. Confusion matrix provide a breakdown error made by our model, right? So confusion matrix basically it break down the true positive, true negative, false positive, and false negative, right? Now we look at all three matrices. So now we had discussed about the precision, we have discussed about the recall, we have discussed about the F1 score, right? So here is an overview of what we have seen. So this is a component of the confusion matrix, right? So this off diagonal value, basically we call this as a type 2 error and this is a type 1 error. So false negative. So it's not false. Just let me check. Is it a false negative or false? Yeah. So this is a false positive, not false negative, right? And this is a false positive. Oh, basically it is written in the inverted way, right? But here we have the formula for accuracy. Here we have the formula for F1 score. We have the formula for recall. Now, if recall also referred to as an TP rate and the sensitivity. TP means true positive rate and sensitivity score. The precision value we have. Here is a formula for precision. Here is a formula for true negative rate or the specificity. So sensitivity is the true positive rate. So TP rate means true positive rate, and sensitivity, and this is a true negative rate and specificity. So how to call this true negative rate? Basically, it's true negative divided by the total number of negative examples, right? And the false positive rate is this formula we have. So we have the formula for false negative rate. So we have the formula for lot of, we can break down our confusion matrix, and we can see a lot of formula over here, and all the formula that we use based on the requirement, and here we can see that, right? Right, and here we can see the cross validation with the different matrices. So we have the lot of scoring, all the scoring matrices that we are using. Now if you are doing the cross validation, you can pass this scoring value, you can pass this scoring list. Here we are passing this scoring list, right? And then after that, here we can see the data frames. So like here we have converted all the scores in the form of data frames, right? Here we can see the test accuracy, train accuracy, test F1 score, train F1 score, test recall, test train recall, test precision, train precisions, right? So we can see our all the scoring value in cross validations, right? Now Now we'll talk about precision recall curve and ROC curve. Now, in precision recall curve, sometimes precision recall curve also called as a PR curve, right? So here now we'll discuss about the PR curve and the ROC curve. Now this all we know that confusion matrix provide this breakdown of the error, right? But when we create a confusion matrix, we use the hard predictions, right? So basically hard prediction means basically we just say that whether this belongs to this class, this example belongs to this class, and so on. But most classifier in scikit-learn provides a predict probability method. That means it gives you the probability score being that specific class. So let's say that if you have the example and your model says it's class A, so predict method says that it's class A. But when we use predict probab method, it will says that your example belongs to maybe 80% as in class A, but this 20% is classified as in class B. So it really gives you the degree of certainty for the predictions. So the question is, can we explore the degree of uncertainty to understand and improve our model performance? So here for now, to understand this, let's see these examples. So we have created a pipeline. We are applying the fit method. We are applying the predict method. This is our classification report we are getting. By default, the model uses the threshold of zero point 0.5. So it uses, again, all we know that this because this is the logistic regression we have, right? It uses a zero point 0.5. So below zero point 0.5, it's a class 0. After zero point 0.5, it's class 1. We know that. So by default, it uses the threshold value of zero point 0.5. And if the predict probab is greater than 0.5, it will say the fraud, otherwise it will say the non-fraud. So again, you can also say in this way. So instead of saying the predict method, which we use directly over here, we can simply say this predict probab, and then we are passing here we are passing the validation data, and then we are saying that greater than 0.5, right? So this thing is gives you the same result as these things, right? Both will give you the similar result, right? And here, if we are using the result of this predict probab with the greater than 0.5, and then we are passing this predicted value into the confusion matrix, we are getting the similar result. Here we can see that this result is similar to this result. So now we know that this is the default that we use, right? So this 0.5 is the default value this predict method uses. Now the question comes, suppose for your own business, right, it is most costly to kind of miss fraud transactions. That means you do not you cannot miss the fraud transactions, right? And here you want to achieve at least the recall of 75% of the fraud. Currently, we have the 62% of the recall. And remember what the recall is? Basically, among all the positive example, how many is actually positive we have identified. That is what the recall is. So consider, we want to consider to be more example classified as an actual fraud, right? So here with the default value of 0.5, right? Our model says that now with this 0.5 threshold value, we are getting the 62% of the threshold, right? Now we want to achieve at least 75% of the threshold. Now one way to do this is achieve by changing the threshold value. So here what we can do is, so now we know that the default threshold value is 0.5, right? We can change our threshold value. So here what we're saying is, so again the key idea is, what if the threshold, what if we threshold the probability at a smaller value? That will help you to identify more example as a fraud examples. So if you set the threshold value, so again remember that if less than the 0.5% is non-fraud. So now we want to increase the bar for the fraud transaction. So here we can lower down this 0.5 value, this threshold value, and here now we want to lower down to 0.1. So now we are using the predict probab method, and now we are saying that if it is greater than 0.1, then those example is considered as a fraud. If it is less than 0.1, then it is non-fraud. And when we are using this, now we have got the recall of 76%. Earlier our F1 score was 72%. Here our F1 score has increased to 77%. Earlier our precision was 88%, but now we have got the precision of 10% reduction, which is 78%. That means our precision value has been decreased. That means now more example is classified as a non-fraud, but we are at least identifying the more fraud example as a fraud, right? So we can use this technique to increase our value, right? Now our operating point. So basically here, when we have used this 0.5 or like 0.1, this is called the operating point, right? So setting the requirement on the classifier, that is a recall of greater than equal to 0.5, is called the setting the operating point. So this 0.5, 0.1, all this is nothing but operating point, right? And this is how we can increase the, or we can change our precision recall and F1 score according to the requirement. Now, what is PR trade-off or precision recall trade-off? Now we know what is precision and recall, and how to change the value, right? But what is PR or precision recall trade-off? So that means, so again, here we have seen that if recall increases, precision decreases. Precision increases, recall decreases, right? So we have to choose between both. Like we have to choose that, do we want to increase the precision or do we want to increase the recall, right? And ultimately our goal is to increase to get the, like if you are neutral over precision and recall, so your goal should be highest F1 score, right? But let's say that we are not neutral, we want to get the specific result, then we have to set a different parameter to achieve our result, right? So the thing is, if you identify more things as a fraud, the recall is going to be increased, right? But you will see more false positive. That means you will see the lesser precision value. Here we can check that. So here what we have done is, we have taken all the value between 0 to 1 with the step value of 0.1. So this is the step, like this is the threshold value that we have chose. So what we have done is, here we have predicted our value with the multiple threshold, right? And then we have stored the result, right? And then for every threshold we have got the precision score, we have got the recall score, and we have got the F1 score. So now we can take a breakdown of this and now we can look at that. And here is the graph of that. Here we have looked at the different threshold value for the different threshold, which is the operating point. What is the precision and what is recall and what is the first score that we are getting. Here we can see our precision value is 0%, approximately 0%, but our recall is 100%. That means what? We are saying that when we are saying recall is 100%, that means we are identifying all the example as a fraud example, right? Now here, now our threshold value has increased. Now we are saying that our recall value is 76%, but our precision value has been increased now. And so this recall value has been decreased, but our precision value has been increased now, right? And here we can see that as you will increase the operating point, you will see that precision value is increasing, right? And as you will increase the operating point, which is the threshold value, your recall value is decreasing, right? So we have to choose the best according to our need, right? So now the increasing the threshold, as we have seen, right? If you increase the threshold, right? So recall value will be decreased, right? But the precision value will be increased. That means if you are saying that this example, like this many example is positive, that means most of the example will be considered as a positive. Now that is what the precision recall trade-off. Now let's talk about PR curve or the precision recall curve. So often when developing a model, right, it's not always clear what operating point is, right? So because the different data set behave differently with the model, so it's not sure which should be the good operating point, right? And to understand the model better, basically it's an informative to look all the possible threshold. So let's say that we do not know which is the operating point, but what we can do is we can look at all the possible threshold, right? And the trade-off between precision and recall curve. So here we can build a plot. So to build a plot, we can use this precision recall curve. We can import this precision recall curve functions. We are using this precision recall curve function. Here we are passing the validation data and the predicted probability value, which is the probability value that we are getting, right? And now this precision recall curve will give you precision, recall, and threshold, right? Now here we are plotting our precision recall value. Basically, it will give you the precision, the different precision value, the different recall value at a different threshold. We have given the label as an precision, recall, and now we are using the plot function. But here we are using this plot function as an O, which is the marker value, and we are only predicting. Here we are only predicting a specific value, right? So here we are plotting this precision score and the recall score, right? So this precision score will give you the specific value, the specific point, and recall score will give you the specific point, right? And and yeah, so basically we are plotting a dot at the threshold of 0.5, and here we can see that this is the value that we have got. This is the graph that we have got based on this precision recall, this multiple value, this plot that we are getting, this plot, right? And when we call this plot function, basically it gives you this red dot. So now we have a different precision value and the different recall value, right? At the threshold value of 0.5, right? So now so this red dot at a 0.5, so at threshold value of 0.5, right, which we can get the recall value of 0.6 approximately and more than 80% as a precision we can get. But let's say that if you want to get the higher recall, if you want to get the higher recall, you have to lower down the the operating point, right? If you want to get the higher precision, so you have to increase the operating point, right? And this is how we can use. So we can take a look at this graph, and then we can understand that which operating point is the good operating point, and based on our based on our requirement, we can choose the best operating point over here, right? Right. If you have the good So if you have this good balanced data, you will see the precision recall curve at this curve, at a very good curve you will see, and then this value over here at top left, sorry, at top right is will be our good operating point. Right? Now, a different classifier might work differently in a different part of the curve, right? At a different operating point. But we can compare PR curve of different classifier to understand these differences. Now we know, now we have discussed about the precision, we have discussed about the recall, we have discussed about the score, right? Now we have discussed about the PR curve. Now we have seen that at a different threshold value, we can get the different PR curve. Now let's talk about the AP score. What is AP score? So often it is useful to have one number summary, right? So if you want to get if you want to summarize this PR plot, precision recall plot, if you want to summarize this, now to get, let's say that if you want to get a good model with the highest recall and highest precision, right? So let's say that if you have the multiple model to choose, so for each model, you need to look at the graph, right? But we have the summary called PR score. We have this method called PR score. Basically, it will calculate a total area of this PR. So basically, it will give you the which model has the highest PR score, right? So this PR score, this PR, sorry, this AP score, basically it will give you the summary of the PR plot, right? So one way to do this by computing the area under the PR curve, right? And we call this as an average precision score. So it's like we calculate the total area under this precision recall curve. If this area is covered higher, that means our model is great, right? We want to cover all this area, right? And for that, we have created a formula which is called AP score as an average precision score, right? So score for the value is 0 means the worst model and the 1 means the best model. Here we can calculate this average precision score, right? And here we can see that our model has 75% of the average precision score. Now we have the 2 point summary, this 2 1 point summary. One is the AP score, other one is F1 score. So the question is when we should use the AP score and when we should use the F1 score. So F1 score is good. So if you already know the threshold value, like let's say that if you have chose the threshold value, right? If you have chose the specific threshold value is the good model for you. Now in that threshold value, if you want to at like if you have already got the threshold value, right, for a given threshold and measure the quality of the predict method. So F1 score is good for a specific threshold value and measure the quality of the model, right? And AP score is good, is a summary across the threshold value and measure the quality of predict probability method, right? So if you are still looking for the best model, like best, like let's say that if you have the multiple model, okay, let's say that if you have the multiple model, now you want to choose which model is the good model, right? For that you can use the AP score. AP score can give you the model. So if the model having the highest this area covered, that means that is a good model. So now that will help you to, this model is going to behave much better compared to all other model. Now that model, now if you want to choose the best F1 score, right? Let's say that, okay, after you chose the model, let's say that if you want to do the hyperparameter tuning, now for that you can use the F1 score, F1 score will help you to good hyperparameter. Now, after you found the good hyperparameter, now you can set the best threshold value. Now you can choose the best threshold value, right? And that way we can build a good model, or we can do the other way around. That means after you set that you want to use the specific machine learning model, then you can choose the best threshold value. So for best threshold value, you can now you can tune the best hyperparameter using F1 score, right? Now let's talk about ROC curve. Now ROC is the another used tool to analyze the behavior of classifier at a different threshold, right? Just like the AP score that we have used, right? So it's a similar to PR curve, right? So sorry, not the AP score, but the PR curve, right? So it contains all the possible threshold for a given classifier, right? But but in ROC, instead of precision and recall, it plot false positive rate and true positive rate. So true positive rate is nothing but the recall, but false positive rate is different, right? So here you can plot it. We can simply import this ROC curve. We can use this ROC curve. It gives you the three things: false positive rate, true positive rate, and the threshold. And here we are plotting it. Here we can see that this is the value that we are getting. Now it is up to us that, so again, this is the threshold value of 0.5. It is up to us that which value we are asking. Like, are we asking for a good for a big recall, or like big false positive rate? So this is the value we have, right? So we have to choose that which value we are choosing. And again, the ideal curve is close to the top left, right? So this is the ideal curve we have, right? So now ideally we want a classifier with a high recall by keeping low false positive rate, right? We want the high recall by keeping low false positive rate. So we want to get the highest recall value that we can get, right? Now, now now we also need a 1 point summary for this. For that, we have this function called area under the curve, or the AUC score, which provide a meaningful number of model performance. So again, you can get this AUC score using this. So here the AUC score is 97%. Now the AUC of 0.5 means a random chance. AUC can be interpreted as evaluating the ranking of positive examples, right? Now let's look at all the scores. So here we are looking at the accuracy, F1 score, recall, precision, ROC score, or the average precision scores. Now we know all about the matrices, right? For again, all this matrices is specifically designed for the classification task, right? Now let's talk about how to deal with the imbalanced data set. So dealing with the imbalanced data set in training set is a difficult task actually, right? So basically, like, again, in the real world, we generally have the imbalanced data only, right? So let's say that if you are talking about the fraud detections, in the fraud detection, we do not have the much example for the fraud. So again, we'll have the imbalanced data set. So for the spam detection as well, we have the imbalanced data set, right? For the ad clicking data, like many people, just only few people, handful of the people just click the ad. That data set is also imbalanced one, right? Now, how do we deal with that? How do we address this imbalanced data set, right? So again, so there are various methods we have to deal with the imbalanced data set, right? And like the method, we have the smooth method, we have the other method as well, but we'll not discuss those over here. But we'll see the other technique here. We'll see the other technique like uh, like class weight parameter. Like we can set a specific weightage for the specific class, like specific weightage for the specific type of the data, right? We can give the higher weight to the data which is more important, right? And also we have to look at which type of error is more important. Now we can also look for, again, like of course this class or like class imbalance is important, right? But if we have the imbalanced class, right, we also have to make sure that which type of error is more important, like the false positive rate is more important to us or false negative rate is the more important to us. We also need to look at the ROC curve or like other threshold value, right? We have to be very much specific, right, that which type of problem that we are trying to identify and which, and we have to be specific that why we are building the model or which type of task we want to achieve by using that model, right? Now how do we handle it? So basically we have the other techniques. We can use this undersampling of the data, we can do the oversampling of the data, or we can do the training process. We can change the training procedures. So by defining the class weight parameters, right, we can change the training procedure of the models, right? And here we'll talk about that. Here, at least, like not at least, but most of the model have this class weight parameter, specifically if they are, if that model is a classification model, then it has class weight parameters. And by default, the class weight is given none, right? None means basically it gives the like if the class weight is none means this means that we are giving the same weightage for both the type of classes or all the type of classes, right? But we can set this class weight parameter. For that you can check out the documentation, but here we can set as a dictionary. We can, so this is the class weight value. We have one thing we can set as a dictionary. We can also set as unbalanced. We can also set the, and the default is the none, right? So the weight associated with the class in the form of this. So we have to say the class label and the weight is. So if you are want to set as a dictionary, we can set the class label and the weight. What are the weight that you want to give, right? Now here, uh, where it is. So here in this model, we are saying we are setting the class weight as in 0 as in 1 and 1 as 10. That means that the 0 class has the 1 weightage and the class 1 has the 10 weightage. That means 0 means non-fraud. So non-fraud, we are giving the 1 as a weight, and for the fraud, we are giving 10 as a weight. So basically, we are saying that the fraud class is 10 times more important than the non-fraud examples, right? This is what the meaning is. So here, again, I'm repeating, the meaning is the non-fraud class. So fraud class is 10 times important than the non-fraud class, right? And this is being set while making our estimator, right? And here we are applying fit, and then we are applying the predict method. So here when we check the classification report, now what we see, again, this is, we are getting the result with the default parameter. With the default parameter we are setting, we are getting the recall of approximately 80%. F1 score is 77% and the precision is 75%. Right? Now we can also check that, again, this is with the threshold value of 0.5, but we can also look at the precision recall curve and we can check that which, like which threshold value can give you the highest recall, right? And if you set the class weight as a balance, right, this will give the weightage parameter as an equal, so each class will be look as an equal over here, right? And yeah, so this is the one way that we can deal with the imbalanced data set. And when we use the balanced data set, here we can say that we have got a very less precisions, right? So this is not the good. So we are giving the equal importance to all the example, which is not the good options, right? And here we are looking at the other value, like the all the parameter we are looking at the balanced, and this is the value that we are getting with the balanced class. We are getting this precision score and the recall score and like other things, right? Now changing the class weight will generally reduce the accuracy. The original model was trying to maximize the accuracy, right? And there are a lot of things that you can do. You can also do the stratified split, but again, stratified split is already there. So when we do the cross validation, by default, it uses the stratified split only, right? And yeah, that's it. That's it. So what we have learned? So we have learned a lot about how to deal with the classification data set, and specifically, if we have the imbalanced data sets, then how do we deal with that, right? And we have this lot of relevant research paper to read it out. Thank you very much.